we're going to do a couple of examples of applications of circular motion. The first is going to be cars traveling in circles. And so we got an example. What is the minimum coefficient of friction between a car's tires and the road for it to travel in a circle with a radius of 20 meters per second? Now, what you have to understand about this is that the force that allows a car to travel in a circle is friction. If there wasn't friction, the car would end up going in a straight line. So a lot of times you see that on ice, a car is driving down a road and tries to make a curve, and since it's on the ice, instead of turning, it just keeps sliding in a straight direction off the road. So if I was to draw a free body diagram of this car, I'm going to do like a front view of it. So the car's coming straight at you. So here's the headlights, here's the tires, here's the car. Okay? The forces acting on it are the force of gravity down and the normal force up. Okay? And the force of friction actually goes towards the center of the circle. We're going to say that this car is going in a circle like this. So the force of friction is going to be in towards the center of the circle. Now, if I do an F-net, once I draw the free body diagram, I'm always left to do an F-net equation. Now, since the car, the normal force and the force of gravity are going to cancel because they're in opposite directions, and my only force that's left is my force of friction. So Ff equals ma. Since we're going in a circle, we can replace the a with v squared over r. So Ff equals mv squared over r. Now, we can go one step farther. If you remember, Ff is mu Fn. So I can replace the Ff with mu Fn is mv squared over r. Now, this Fg is equal to m times g. So I know this Fn is also going to be m times g. So now I get mu mg equals mv squared over r. This cancels here, this cancels here, and now I think I'm going to be able to solve the problem because I'm trying to find the coefficient of friction. So, mu times g is 10 equals v, so it's a speed of 30 meters per second, over r, which is 20 meters. So now I have 10 mu equals 900 divided by 20. So then 10 mu equals 45, and then mu would be 4.5, which is kind of a large value. I guess I didn't think about whether to make this problem make sense before I made it up, but that is how you handle something, a car traveling in a circle. The force pointing toward the center of the circle is Ff, so when you do F-net equals ma, the F-net is Ff. For an orbit, if I was to think of the Earth traveling around the sun, for instance, the free body diagram is actually very simple. The only force on it is the force of gravity. So when we do our F-net equation, it's going to be that the force of gravity equals m, and then again for our velocity we'll do v squared over r. Now, we have an equation in this unit that's new. For the force of gravity, it's going to be g m1 m2 over r squared equals m v squared over r. Now let's take a look at this. We have the Earth being orbited by a satellite. Okay? And we can change this to g m Earth m satellite over r squared equals. Now the m here is the this is a circle equation, the mv squared over r. So the m on this side is the m for the thing going around in a circle. So in this case, it's going to be mass of the satellite v squared over r. Now we can do some canceling to simplify this, okay? I could plug numbers in here right away, but it's going to be quicker to simplify it first. So anything I see on both sides I can cancel. So I have ms on the left and ms on the right, so I can cancel it. I have r squared on the bottom on this side and r on this side, so I can cancel the squared with one of the r's. And this simplifies to g me over r equals v squared. And now I can start plugging some information into this. So g is a constant, 6.67 times 10 to the minus 11th. The mass of the Earth we're given up here in the problem is 6 times 10 to the 24th. Divided by, the radius is 7 times 10 to the 8th. And that equals v squared. Now, finishing this off, I get 756 meters per second is v. So this is actually a useful problem. We can figure out how fast the satellite has to be going in order to orbit the Earth if we know how far up it's going to be.